we're looking at a cheap and effective, in fact, DC PWM controller. You can use it for locos, or you can use it for any motor, for windmills or whatever, water mills, any DC motor really. I thought I'd do a quick word on what PWM is, just to refresh it for ourselves. When you're working on DC, then the top graph shows you you'll go between nothing and 12 volts. And sometimes you're working at full speed, in which case you're putting 11 or 12 volts out onto the track. If you slow down, you cut the voltage down to 4 or 5 or whatever, and you get a slower speed, cut the voltage down again, and you get an even slower speed. The problem with ordinary DC motors work that way is they work fine at the fast speed and the mid speed. They can be not so efficient at the slow speed, and it leads to, as you all know, in fact, locos stalling or problems taking off. They're hard to overcome the stiction. So we want to avoid that, and how we avoid it is in the bottom graph. It's called pulse width modulation, and essentially we're modulating, which is the M, the width of the pulse. So we're putting out 12 volts all the time, but only in bursts. So if you put out a pulse of 12 volts with only a short break in between dropping to 0, then most of the time the effective value is near 12 volts. If you look at the top one, if you get very short pulse widths, then the amount of current that's going to go through the motor is much reduced compared to the bottom. And again, mid speed would be, say, half the time on, half the time off. The benefit of PWM is that when you get to the slower speeds, you're still putting out pulses of 12 volts. And those 12 volt pulses help for slow running, and they also help for overcoming stiction. In other words, going from a stationary position to a moving position. So that's PWM. So how are we going to achieve it? Well, there's our motor. We have an oscillator. It's going to produce those pulses. But on its own, the oscillator, generally speaking, doesn't have the capability of driving high current motors. Its output isn't up to it. So normally what you do is you put in between a driver, something that can take the incoming pulses from the oscillator and in turn generate higher current to the motor that you could get from the oscillator on its own. So there's two components for a DC PWM controller, oscillator and driver. And that got me thinking, there's already a kit in the kit locker for a LED dimmer. And it works with pulse width modulation. And what it's doing is it's using the pulse width to change the illumination on the LED strip. So the wide pulses mean that light's on all the time. Narrow pulses mean it's on for shorter times, but your eye compensates and sees it on all the time, but dimmer. Right, so we can use it with everything in between narrow pulses to wide pulses to change the illumination of a single bright LED or a LED strip. And that's what that was designed for. And I thought, well, why can't that be used for a local? So there's a circuit for the kit as you buy it from the kit locker. The bits in black are the actual oscillator itself. There's the pot that changes the pulse width. The output is a square wave with varying width of pulses. And normally in the kit, it goes to a power transistor so it can switch the whole LED strip if necessary. I've done that in red because we don't want to be changing a LED strip. We want to control a local from this output. So that's the board you get with the kit. The components you see in red on the right, we don't need. They're only to handle the LED strip. So the output coming from here that would normally feed the power transistor, instead we want to take to the module that controls the motor itself. A couple of other changes. We normally feed this with 12 volts, but we're going to feed it with 5 volts instead, because this module, the 293D module, expects 5-volt pulses coming in. So we don't want to generate 12 volts out of here and damage the module. So that's the other mod is that as it stands, this LED dimmer runs at 220 or something hertz, a couple of hundred hertz. We might want it to run at a lower frequency. Generally speaking, we find they're better at 100 or 50 hertz and so on. So if you added an extra capacitor on top of the one that comes with the kit, you can get to run slower. So that's where we are with the oscillator. Let's have a look. So here's the part build. The left-hand part is the oscillator. I'll just connect up the scope. And you can see the trace is very narrow pulse, but if I change the pot, the pulse gets wider and wider and wider until it's almost fully on. So I can go from a very high mark space ratio to a very, very low mark space ratio. And we're running at 100 hertz approximately. So that's the oscillator part. We now have to drive the motor itself, and we're looking at the 293D chip. You can buy it on its own, as you'll see later, or they come already built on a module. That's the most common one. So you've got all your connections for controlling it and your output connections to go to motors. The one up here is simply two 293Ds and a chip in between to control it if you want to have multiple motors. But we'll look at this module and we'll look at this individual chip. The 293D as a chip is already covered in one of the videos on our website. Just look for the 293D. But as a recap, it can handle from up to 600 milliamps on its output continuously, 1.2 amps as a peak. But if you want to, it's got more than one output, you can parallel them up, in which case you can have 1.2 amps and 2.4 peak. So it can handle most motors that we'd be coming across. And it can handle, as an input, motors as low as 4.5 working up to 36 volt working. Most of the time we're looking at 12 volts, but let's have a look. That's the chip there. There's the pins on it. It doesn't have its own heatsink, but it has 4 different ground pins. And the idea is you use either the copper tracks from the Vero board or a copper part of the PCB to act as a heatsink. What's inside it? That 4 different amplifiers actually. You could run 4 motors if you wished. There's your 4 0 volts there. And there's what they call a truth table. Whatever you put in is what you get out. If you put a high in, you get a high out. So if I make pin 2 go high, pin 3 goes high. we make pin 2 low, pin 3 goes low. Simple as that. So you get 4 in the one package. But there are other pins called enable pins. You can see it in red here. This pair here will not follow in and out until it is enabled. Here's the enable pin. If you make the enable high, then everything I mentioned earlier, high, high, low, low, works. The minute you take an enable pin low, it's effectively the output is high impedance, as if it wasn't there. You get no output from pin 3 or 6 or 11 or 14. We'll come back to how we use enable in a minute. You'll notice there are 2 power supplies. There's 5 volts, which is what we're using for the logic inside the 293D. But your motor could be, as you saw, 4.5 volts, it could be 12 volts, it could be 9 volts, it could be an 18-volt motor. So you have a separate supply here. So if you're running a 12-volt motor, you'd put 12 volts in pin 8. If it's a 9-volt motor, you'd put 9 volts in pin 8, but you also have 5 volts in pin 16. Knowing that, we're good to go. How can we control a motor? Well, clearly we can make pin 15 go high, not make pin 14 go high, and bring the motor on. We could do that. But then how would we reverse it? That way it'd only be the motor on or off. We need more than that. We want to go forward and reverse the locus. And what you do is you use 2 of the outputs. So if I make this pin 15 go high, 14 goes high. But if I make pin 10 go low, 11's low. So I've now got a high and a low. The motor's going to rotate. And when I say high or low, I'm not talking about the 5-volt high or low. I'm talking about this motor supply going high or low. So if it's 12 in here, you get plus 12 here and 0 there. So right now I've got plus at the top, 0 here. If I reverse it, I've now got the motor going in the opposite direction. So by changing the inputs in pin 10 and 15, I can make the motor go forward or reverse. And that's what we intend to do. That's taken from the 293D's specification sheet. As you saw earlier, if the enable's high, then whatever you put in comes out the other end. So there's, if I make 1 low and 1 high, as you saw, that's that going to rotate. If I make it high and low, it'll turn in the other direction. If I keep the enable high and turn them both low or both high, the motor just stops. It's got a fast stop because the enable's still high. It means the back EMF will come into play and make it stop quicker than it normally would. If you take the enable low, it still stops, but it's what we call free running. So knowing that, making 1 high and 1 low, we can make it turn in either direction. That's all we need to do. We put a pull up onto pin 10. We put a pull up onto pin 15. Have one of these center off switches. And if you throw the switch, say to the left here, you're bringing that one low and that one's still high. It'll go in one direction. If you throw the switch the other way, that's now going to be brought down to low and that one's high. It'll go in the other direction. So with a simple single pole double throw center off switch, we're able to control the direction and stop and start of that motor. No other fancy circuitry. Now I mentioned earlier on that the enable will switch on or off, and it usually goes +5 to switch it on. But what happens if I feed in the PWM from the lead dimmer? It means those high and lows here will be switching all the time. So in effect, it's not high and low, it's low and a switched high, pulsed high. We've now got pulse width modulation on the motor. There's the chip itself on a board. It comes with 4 outputs. It's got its 4 inputs. There's the enable pins of each half. Right now, they've been taken to another jumper, but if we take these off and instead feed these enables from the lead dimmer, we fed PWM into this. And that's it. There's the existing lead dimmer. If you want to, you can change the frequency. Instead of 12 volts coming in, it's now coming in from a 5-volt regulator, which also feeds the 5 volts into the logic of this chip. And because we're working with a local here, I'm putting 12 volts straight in for a 12-volt local. And those two go to the track, and that's it. There's your changeover switch. There's the pot that comes with the kit. And that's it. The left-hand side is the original lead dimmer. If you're starting from scratch, you wouldn't be using 2 lots of 100 nanofarad. You'd be using 1 220 nanofarad to get the lower frequency. There's your switch between forward and reverse. And there's the power to the track at 12 volts. That's it. Looks like that. If you want to, you can mount it all on the same bit of aero board. The left-hand bit is still the original lead dimmer. We've just changed the components on the right-hand side, and it's now a PWM controller. Right, let's have a look at this. I've now completed the second part, the 293D driver. Still standalone, it's not connected to the oscillator. 5 volts come in for the logic, and I've connected the 12 volts as the motor supply. I've also connected a single pole, double throw, center off switch, such that when I throw it in one direction, it'll go clockwise, stop, counterclockwise. So I can control the direction and make it stop, but at this point I can't control the speed until I connect the oscillator's output to the input here. Okay, let's do it then. I have now made the link between the output of the oscillator and the 2 enable pins of the 293D. So if I now control the speed, and direction, that's it. So there's 2 ways of doing it. You can actually use the 293D module, or you can just use a 293D chip and put it on the same bit of aero board. And let's just see how well it performs. That's it, with the wheels cleaned and the track cleaned. That's a 009 local sitting in N gauge type track. In fact, It's so slow. I did a calculation. I looked at that video and I counted how many sleepers it moved over time. And it moved 20 sleepers in 40 seconds, which works out at a scale speed of 0.38 miles per hour, which I think is impressive in MD's language. If you can build a PWM controller that makes a local run at less than half a mile an hour, I think we're doing well for £2.50. And that's it. Are there any questions or comments or suggestions?